Okay, hello and welcome. It's SFU Math 232. It's Brenda speaking. We're going to talk today about section 7.1, basis and dimension. So what we want to do is make the idea of dimension, which we've brought up informally a lot of times, a little bit more mathematically precise. So we want to recall as we get going here what the what it means for a certain number of vectors. What is the span? So here you notice we have S vectors, V1 through Vs, and then we define the span of those vectors to be all possible linear combinations of the vectors. Okay, and you'll recall also that the span is a subspace. Okay, so let's take a look here, a subspace here defined W. So the subspace is defined to be the span of these three vectors here. And then what we're going to do is show that actually the same space, subspace W, can also be represented by this span here. Okay, so let's take a look at the first, not really a definition, but the first, I guess maybe say the first definition of W as the span of those three vectors. So that tells us that W is equal to C1 times 1, 0, 0, that's the first vector there, plus C2 times the second vector, 0, 1, 0, plus C3 times the third vector, which is 1, 1, 0. So for all values of C1, C2, and C3 that are real numbers, that all those vectors together are W, and that is a subspace. Now, we will notice in this case that W can be written, not W, sorry, the third vector in here, that vector there, let's put it here, that vector can be written as a linear combination of the other two vectors. So I could write it like this. Okay, that means I could write W in this way. It'd still be C1 times 1, 0, 0 plus C2 times 0, 1, 0 plus C3 times, now instead of putting this guy here, I am going to put this C3 represented in this way, 1, 0, 0 plus 0, 1, 0, like that. And then I can combine constants, and I can write W like this, C1 plus C3 times 1, 0, 0, and C2 plus C3 multiplied by 0, 1, 0. And then these things here, I could either rename if I want, or I can just see that those are just numbers. So I could just make some sort of definition. I don't know, let's call it like this. T1 equals C1 plus C3, and T2 equals C2 plus C3. Then I would have that W is equal to T1, 1, 0, 0, and T2, 0, 1, 0, like that, where T1 and T2 are real numbers. So that in fact shows you that W is the span of these two vectors here. Okay, and so the subspace W can be represented by either one of those statements. Clearly, this one in some sense seems, well, it's slightly less complicated. There's only two vectors in it instead of three. All right, so we could then ask ourselves, can we remove another one of those? And the answer in this one is no, we cannot. This guy here is not a linear combination of that guy. It's not a scalar multiple of it. Okay, so what we do then is we identify that sometimes we can remove some vectors from our span statement and nothing changes. The subspace stays the same. So, and then sometimes we cannot. And so we're going to identify that here, and we're going to call that by a special name. So if we have a set of vectors, just like we had above, v1 through vs, and we have from that a subspace V, we call the vectors a basis for V if the span of all of them is V, as it was before, and if the vectors in this set here are linearly independent. Okay, so let's just formalize that a bit here with our example by saying, so now consider W, which we've identified is also the span of these two guys. Okay, and I ask myself, does C1, C2, not 0, exist such that C1, 1, 0, 0 plus C2, 0, 1, 0 equals 0? And I look at the first row, so I'm looking here at row 1, like that. C1 plus 0 times C2 equals to 0. That tells me that C1 has to be 0, and then I can just look at the second row, and then that tells me that C2 has to be 0. So the answer to that question is no. C1 and C2 have to be 0. Therefore, 1, 0, 0 and 0, 1, 0 are linearly independent. Okay, and that means then that these two vectors, 1, 0, 0 and 0, 1, 0, are a basis for W. Okay, it's what you need to be able to get to be able to form as linear combinations all of the vectors in W. It's what you need, and it isn't anything else. There's no additional superfluous stuff that you can get rid of. Okay, what is the basis for a subspace L where L is a line through the origin in Rn? Let's just draw it in R2. Okay, there's a line through the origin in R2. So this is the R2 example. There's a line through the origin. What would we need to have a basis for that? You need one vector lying on the line. So I could just show you what a basis vector would look like. So for example, that would be a basis vector. That would be one basis vector for the subspace L, where L is that line. Okay, I could have it's not unique. Bases are not unique. Here's another basis vector. There's another basis vector. That basis vector also, the span of that basis vector is also L. This line being L. Okay, so the idea is, though, we only need, in this case, one vector. We don't need to have two of them. Okay, so I'll say it this way. Vector V is a basis for L if it is any non-zero vector on L. Okay, the vector V in the general case, in the Rn case, V will have n components. Okay. All right, find a basis for the subspace P, where P is a plane through the origin in Rn. Okay, let us just again go back to a lower dimension, just not, well, at least not in general Rn. Let us just take a look at R2. Like here, we'll draw R2, and we've got X, Y, and Z. And we imagine, say, for example, the plane here. the xy plane. So what would we need to be able to span that plane in R3? Sorry, why did I write R2 here? This is R3. So the plane is a two-dimensional thing. What do we need to span it? We need two vectors. They must be non-zero. So we need two vectors. One won't be enough. They must be non-zero. They must be linearly independent. It's no use picking one vector that is a scalar multiple of another. We don't gain anything that way. So for example, we could pick two vectors like this. We could have v2 along here, and we could have v1 along here, and then those two vectors would span the xy plane. So I would say then here, we have here now, we could be thinking now in the general case, but v1, v2 are two linearly independent non-zero vectors, and that form a basis for P, a plane. Okay. All right. So if we take a set of vectors and we want to show it's a basis, what do we have to do? So we have a set of vectors and we want to show that that is a basis for Rn. So we have to ask first, does it span Rn? Okay, it has to span. And then are the vectors linearly independent? So we'll just answer both of those questions, and then that will show that this set is a basis for Rn. Okay, so what I'm going to do is I'm going to say take some vector v, arbitrary vector v, in Rn. Okay, so v will look like this. These are the components of v, like that. Okay, so I can say then I can write v this way. V could be written like this: v1 times e1 plus v2 times e2 plus dot 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 plus vn times en. Okay, just to recall so we know what we're doing here, e1 is this guy, all zeros, and then e2 is, okay, to the end, and e3, etc. Okay, like that. Get to the end. Okay, so we can write our vector v as a linear combination of the vectors in that set, e1 through en. And the choice of v was arbitrary, so every vector in Rn can be represented this way. So therefore, this set e1, e2 dot 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 en spans Rn. Okay, that's the first thing. Now we have to show that the vectors e1 through en are linearly independent. So I'm going to say then, when does c1 times e1, looking like that, plus c2 times e2, looking like that, plus c3 times e3, looking like that, plus dot 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 plus cn times en, looking like that. When does that equal 0? Well, from the first row, I can see that that forces c1 to be equal to 0. From the second row, C2 is forced to be 0. And that process continues and down until Cn is equal to 0. So in order for this statement to be true, all of those constants C1 through Cn have to be 0. Therefore, E1 through En are linearly independent, and we are finished. We've showed that it's a basis because it spans and it's linearly and the vectors are linearly independent. Okay, so when we use these vectors, here the unit vectors, we call that the standard basis for Rn. The subspace that consists just of the 0 vector has no basis. Kind of sounds funny, actually. Okay, so if you are doing a problem and you have a choice for your basis, you almost always want to choose the standard basis. It often makes the calculations just more obvious and easier to execute. All right. Let's get a theorem in here. So if we have some set of vectors, here's our set S, and there's our vectors V1 through Vs. It's a set of 2 or more non-zero vectors. Then S is linearly independent if and only if, for some I, vector Vi is a linear combination of its predecessors. Okay, we'll just prove this. So what we're going to do is we're going to take Si in the set from the set S. We're going to assume that Si is a linear combination of S1 all the way to Si minus 1. Okay, that means, of course, that we can write it like this. Si equals to C1 S1 plus C2 S2 plus dot 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 plus Ci minus 1 Si minus 1. And we, with at least C1 Ci minus 1 not equal to 0. At least one of them not equal to 0. At least one not 0. Okay, and therefore we can just simply kind of rewrite in some sense. We are like this, and move the Si to the other side. With not all Ci's non-zero. Okay, therefore S is linearly independent. That's one direction of the proof. Sorry, therefore S is linearly dependent. Okay, the constants are not all 0. Okay, now we go the other way. We assume S is linearly dependent. And that means C1 plus V1, C2, C2 V2 plus dot 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 plus CS VS is equal to 0 for some C1 dot 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 CS not all 0. We have a linearly independent set. Linearly dependent set. Okay, so then what we do is let Ci be such that I is maximum for Ci non-zero. So we just choose the constant Ci that is the largest, so that this number is the largest and non-zero. Okay, then we can easily observe that VI is going to be equal to C1 over CI times V1, and you go through them all like that, and you get up to C I minus 1 over CI V I minus 1, and then we are done, right? So we have then said, okay, we have now shown that that the ith vector can be expressed as a linear combination of its predecessors. Okay, so we have here now 3 vectors, and we want to show that they are linearly independent. Okay, so I mean, previously we've done this. So for example, this would be a way we've done this previously. So previously we showed this thing here, 3, 0, 0, 0, 4, 6, 0, minus 2, 2, had only the trivial solution. Well, that was one way of showing that. Here, so we can just look at it just slightly differently here. We can say start with V1. That is that guy there, 3, 0, 0. Okay, it's just one vector that is linearly independent. And then what we do is we look at V2, which is equal to this guy here, 0, 4, 6. And you can see that V2 is not a linear combination of V1. So look at V2, there it is. So you can see that V2 is not equal to KV1 for any K. Okay, so now we've got that these two are linearly independent. So now we know that V1 and V2 are linearly independent. Okay, and now we ask, we're continuing this process of adding another vector to the set and seeing whether we maintain the linear independence or not. So now I'm gonna take a look at V3. A linear combination of V1 and V2. Ask myself that. So I'm asking, is V3, can I write V3 as C1 V1 plus C2 V2? That's, can I write V3 as a linear combination of V1 and V2? Is that possible? Okay, so I'm going to simply look along the first line right here. There's the first line. That's going to, if I'm going to have 0 equals 3 times C1 plus 0, C1 is going to have to be equal to 0. Okay, then I will look along the second line. I'm going to ask, okay, minus 2 times, what do I have to do to make minus 2 equal to 0 times C1 plus 4 times C2? That is going to force C2 to be what? Minus 2? Yep, minus 2. Okay, but that would imply, since C1 is going to be 0, this guy's toast, that would imply that, what would that imply? Hang on a sec, maybe I won't do it that way. Maybe I'll say, now let's just take a look at the third row. Well, let me just say what it would imply. It would imply that V3 is a scalar multiple of V2. This means this thing here implies, these two things together imply that V3 is equal to K times V2. And I can look at V3 and V2, and I can see that that is not the case. Or I can take a look at this final line here and see that this guy right here, 2 is not equal to 0, 2 is not equal to 0 times 0 plus what is C2? Minus 2 times 6. Okay, so they are linearly independent. Okay. We have a existence theorem here that if we have a set V, it's not it's not just a zero vector. It's a non-zero subspace of Rn. So V is not just a set, actually, it's a subspace of Rn. Then there exists a basis for V that has, and this is a key point, at most n vectors. So we have some subspace of Rn, and then it will have a basis, and that basis will have at most n vectors. Okay, so this is we can just show you that we can construct this, and that constitutes the proof. It's done this way. We take a vector v1, that'll be in V, and then we say if V is the span of v1, we are done. Because we've found a set of vectors with one vector in it that spans the subspace, and we're finished. Okay, if it doesn't, then we continue, and we just keep going like this. Let v2 be in V such that v2 is not a scalar multiple of v1. Okay, and then we ask the same question. If V is the span of v1 and v2, we're done. Okay, and you just keep going until you stop. At each time, choosing another vector that is not a linear combination of the vectors already in the set. And you keep going and going and going, possibly stopping, and then you'll as you're getting nearer to the end, as you're getting to the end, you'll take the nth one, and you will have that nth vector that you add not equal to a linear combination of the previous vectors in the set. Okay, and then you will potentially, you will stop, because when you potentially go to add the next one, bn plus 1 will be linearly independent, will be linearly dependent. Okay, why? Because a linearly independent set in Rn has at most n vectors. Okay, that we have that was a theorem from well time ago. That is on page 131, theorem 3.4.8, which basically says a set with more than n vectors in Rn is linearly dependent. Okay, so that we're guaranteed the existence of this basis for the subspace, and that it will have at most n vectors. Okay, with this at hand, we're going to then say what is a dimension, basically. So suppose we have a non-zero subspace of Rn, we're calling it V. Then we can have a basis in more than one way, but it doesn't have to be the same vectors. But every single one of those bases will have the same number of vectors. Let me just draw a quick example here to illustrate that. Imagine we have here, we want to have a basis for R2. We want to have two vectors. We're going to make two vectors such that the span of those two vectors is all of R2. So I could do it like this if I want. V1, and that would be the standard basis, V2. And then these, I'm going to have this guy equal to 1, 0, and then this guy equal to 0, 1. Okay, so the span of V1 and V2 is R2. Okay, so those two vectors, they're linearly independent and they span R2. So those two vectors there, V1 and V2, are a basis for R2. Now, I can do the same thing with two other vectors. Yeah, here like this. I could take this vector here, V1, like that, and this vector here, V2, like that. And if I imagine all linear combinations of V1 and V2 here, you will see that also whatever these two vectors are, I don't know, let's just say this is the vector 1, 1, and this is the vector -1, 1. Well, then I'm saying for this new example, the span of V1 and V2 is R2. V1 and V2 are linearly independent. So this V1 and V2 is also a basis for R2. Clearly they're not equal. But the thing that is equal is that there's two vectors in each. So you notice there's two vectors here and there is two vectors here. So any set of vectors that are spanning R2 will that are linearly independent will have two vectors in there. So that's what this is telling us. Okay, so we got every basis for a line has one vector, every basis for a plane has two vectors, and every basis for Rn has n vectors, which we just saw. We just had the R2 example. Always a great idea to use R2 and R3 to try to visualize what's going on. Okay, and basically what we're now going to say is that the number of basis vectors is the dimension of the subspace. Okay, so here it is. The dimension of a non-zero subspace of Rn, which we have a little symbol to denote dimension of V, is the number of vectors in a basis for V. Okay, and when we also say that the zero subspace has dimension 0. Okay, so a line through the origin has dimension 1. I mean, here the basis for a line through the origin has one vector, right? So that means it has dimension 1. Every basis for a plane through the origin has two vectors. That is dimension 2. And every basis for Rn has n vectors. That is dimension n. Okay. Next thing to recall and sort of reframe in a slightly different way is that you will recall, we've done this lots of times, we can have the general solution for a system of linear equations, and when this guy here is a 0, that is, we call this a homogeneous system, and we can always express the general solution, the vectors x that solve this. So these vectors x, which make this this statement ax equals 0 true, can be written in this form right here as a linear combination of some number of vectors s, and you'll recall that these parameters here are coming from the free variables. Okay, so now what we now do is define this thing here, the canonical solution. So the vectors v1 through vs, these guys here, right here, from which we can concoct all of the solutions to the homogeneous system, those vectors are called the canonical solutions of ax equals 0. And you can see how you get them. I mean, you here to get v1, so v1 happens x is equal to v1 when what? t1 is 1 and t2 through ts are 0. Okay, so those canonical vectors which we get in the solution, those are linearly independent and they span the solution space. And so as a result of these two conditions here, linearly independent and span, they are then a basis for the solution space, which we call the canonical basis. And the dimension of the solution space is little s. So little s is the number of vectors. So we have here, this is the number of vectors. Okay, so we have these vectors here, v1, v2, blah, 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 vs. There's s of them. That is the dimension of the solution space. Okay, just that is our definition of dimension. Okay, so we're just going to take a bit of an excursion here maybe. What is the dimension of a hyperplane in Rn? So what this is, what we have here is that in R2, a hyperplane is a line with dimension 1. In R3, a hyperplane is a plane with dimension 2. Okay, so what happens as we keep going, in R4, a hyperplane has dimension 3. Okay, and so in general, in Rn, the hyperplane subspace of Rn has dimension n-1. Okay, and in our Euclidean type space, that the hyperplane divides the space into 2. So example, in R2, we take some line through the origin, and that divides the space into 2, this part over here and this part over here. When we have a three-dimensional situation here, we take a plane, let us say it's the xy plane here, and it divides the space into 2, the stuff that's up here and the space that's down here below. Okay. So that's that. The dimension of the hyperplane in Rn is n-1. Okay, that's it for this section. It's a little bit of a shorter section, and I'll be back with section 7.2 shortly. Thanks, guys. Bye.